Okay, study unit 5, lecture 4. So lecture 4 and lecture 5 are concerned with DC MMF in converter transformers. So this is particularly true for half-wave rectification, where controlled or semi-controlled or even uncontrolled rectification is notorious for producing a DC MMF in the transformer. Additionally, triple N harmonics are also induced in the neutral line of the transformer coil. So the triple N harmonics are defined as harmonics which are odd multiples of the third harmonic. So it would be the third harmonic, the 9th harmonic, 15th harmonic, and the 21st harmonic of the AC signal. These triple N harmonics are what are known as zero sequence harmonics, and what happens is that they are additive in phase on the neutral line of the transformer coil. The most obvious disadvantage of having these currents in the neutral are that the currents can be quite large and can lead to heat and can damage the transformer or present some other electrical hazard. So for these study units, some assumptions have to be made. The first is that the DC load current is constant load current, the load inductance is assumed infinite, and finally the transformer is assumed to be linear. The final assumption that gets made is with regard to the AC source signal, which is assumed to be a perfect sinusoid. So the first transformer that gets considered is one that's got a singular primary winding and then two secondary windings. So this is in fact the half-wave rectifier from earlier in the study unit. Here is the primary coil, here is the center tap, two secondary coils, the two switching diodes D1 and D2, followed by the inductive component of the load, the resistive component of the load, and the return path back to the center tap of the secondary coil. Shown here is an alternative coil arrangement. It still consists of a primary and a secondary core, except the primary core consists now of two half-wound cores, while the secondary windings remain the same. So for both these transformers, the ratio of the primary to secondary windings is the same. So the transformer in example A has 3 limbs, whilst the transformer in example B only has 2. In fact, this is actually a circular core transformer. The 3-limb transformer is made of multiple materials in laminations, whereas the circular transformer can be made from a single piece of rolled steel. The first advantage of using this circular core is that the single piece of steel has better magnetic properties than the laminated steel construction. The 3-limb transformers, all the windings are along the central core, or rather the central limb. The MMF of transformer example A is simply the current in the primary multiplied by the number of turns in the primary coil plus the difference between the current in the two secondary coils multiplied by the number of turns in those secondary coils. This equation can be rearranged to give the current which is present in the primary coil. So the difference between the two secondary currents IS1 and IS2 is alternating, which means that if the MMF is 0, the alternating IS2 and IS1 difference will result in a primary average current of 0 as well. So what this means is, because the input is a sinusoid, on average the value of the sinusoid is 0 around the origin, and if the difference between the current direction between the two secondary coils also alternates, means on average that they are also 0, means that the net MMF generated in this transformer is 0 as well, which is shown down here on this graph. So in the single core case, where all the windings are around the center of the transformer, the MMF was common to all the coils. For the circular core case, or the 2-limb case rather, there is an MMF for each primary and secondary pair. Because the coil ratios are all the same, and because the primary coil is linked, MMF1 equals MMF2 is equal to MMF present in the primary coil due to the MMF1 is given by this equation here, which is minus the primary current multiplied by half the number of windings present in the primary coil plus the current in the secondary coil multiplied by the number of windings in the secondary coil. So a similar expression can be derived for MMF2, and then equating all the MMFs together as above here, the primary current can be derived as the number of secondary coils divided by the number of primary coils multiplied by the difference between the first and second secondary coils. So to apply these equations, every pi radians one of these the relative equation will be applied, and then the MMF as well as the output currents can be calculated and plotted. So once again, because the currents are alternating through the diode switches, this difference here, IS1 minus IS2, will alternate, which means that the primary current will alternate between some low value and then some high value through the entire cycle before repeating itself once again. When this is averaged out over many cycles, it results in a DC bias MMF equal to 1/2 NS multiplied by the output current. So one way to see how the MMF affects the performance of the transformer, or rather the design characteristics of the transformer, one needs to look at the power rating for the secondary and primary coils in the transformer. So for example A, where there's a shared core, the primary power rating is 1.11 times the desired output power, and for the secondary coils the power rating is 1.57 times the desired output power. What this means is that for a specific design that the designer would like to use, for a specific power output rating, the primary coil needs to be 11% larger than ideal, and the secondary coils need to be 57% larger than ideal. Finally, the overall power rating of the transformer needs to be 34% higher than the desired power rating. These equations apply to both cores, so essentially on paper both cores have the same power factor, except the toroidal core has the undesired MMF bias. So what needs to be done is to find a way to wind a single toroidal coil in such a way that the DC MMF bias is 0. In this way, the advantages of using a toroidal core can be harnessed above those of using a laminated core. So shown in this diagram is a toroidal single core transformer, which makes use of a zigzag winding technique in order to have a 0 bias MMF. So what's been done in this topology is that the secondary windings have been allowed to cross over each other. So by using a zigzag pattern, the MMF which is present in each limb of the transformer will now affect all the coils and not just pairs of coils. In other words, both secondary windings will be affected by the MMF in the first limb, and both secondary windings will be affected by the MMF in the second limb. Since the primary winding is around both limbs, it is also affected by both MMFs. So writing out the MMF mathematically for both limbs gives two very similar equations here, but with a distinct change in sign between the first limb and the second limb. What this means is that when the primary current is calculated, it is not a function of the net MMF which is present. This means once again, as the difference between the currents in the secondary two coils alternates, the total primary current average will be 0 and thus result in a 0 bias MMF. So this concludes this lecture. The following lecture will have a look at the three-phase characteristics of three-phase transformers.